Okay, I probably should have brought a projector, but right now I've got the wiki open. Mike has got his equipment sizing spreadsheet open, so we've got, it's going to be a team effort here. So we'll kind of base this off his equipment. And I'm just looking at the P&ID map that's posted on the wiki just to understand like what's the scope of what I want to put on this P&ID. So I'm going to do sheet 5, you guys. And that is the 3-phase separator, a couple of heat exchangers, and the 2-phase separator. I figure that's not a bad start anyway. And if it looks like it makes sense to move stuff around, like if we want to move one piece of equipment from one sheet to another, that's fine. I'm almost looking at sheet 3 thinking we could almost move sheet 3 onto other P&IDs. But let's see how this goes for congestion. Like a typical rule of thumb for a really professional P&ID is like 1 or 2 pieces of equipment per P&ID. We tend to get a bit more on the P&IDs because we don't have as much detail in terms of the piping. So the first thing you want to do really is gauge what's on the P&ID, so those pieces of equipment. And then I would say get yourself an 8.5 by 11 sheet of paper and sketch out a rough kind of layout on the piece of paper, just so you kind of know where the equipment should be. So let me just kind of quickly do that. All right. So we have a 3-phase separator that we're going to need to get on here. And what I'm trying to do is I'm trying to lay the equipment out roughly in the elevations that it's going to be, and also try and give myself enough space around the equipment that I can get all the instrumentation in. So the first thing on this P&ID, everything comes in from the P&ID or off from the side of the P&ID, and we're essentially going to go into our 3-phase separator. So I'm just going to basically, that seems like a good spot for it. And then if you follow the oil through the system, it's essentially going to go into some sort of a heat exchanger. So whether I go up or down, and we've got a 2-phase separator in here. The 2-phase separator basically goes right off the sheet, and so it can be right on the side of the P&ID. So it's going to go there, and we are actually, are we flashing? Yeah, we're flashing, right? So we're going to end up having to go into the one heat exchanger and then come out. So let's maybe just kind of roughly put it there, and like that. Okay, so that's going to give me about all I really need. There is another heat exchanger in there. Yeah, there's another heat exchanger that essentially can kind of go there. Okay. Okay, so that's a start anyway. If you're doing this on computer, well, actually, it still makes sense to just get a rough idea what the thing is going to look like first. That's going to go off there. That's going to go off there. That's going to go off there. This is going to come in here, and it's going to go up through there and off like that. Okay, I think whoops. That's good enough. That's good enough for me that I can get started on it. Make sure you have a title block. So this is going to be the algae biodiesel. Okay, P&ID, separator P&ID. It's sheet 5, I think I said, right? Yep. Sheet 5, and it's drawn by moi. Got that? Okay, let's do it. So first thing we want to do is we want to get the equipment laid in here. I'm going to draw it fairly large. I know it's a three-phase separator. Like that. A couple of different ways to do three-phase separators. I can look at the wiki. How did you guys do your three-phase separator? With weirs or a boot or how? With weirs? Yeah. Okay. I think this is one that I want to do with a boot, and I'll explain why. Let's put a boot in. Like that. Be good to get it a little more level, wouldn't it? Okay. Not winning any awards for graphics, am I? Okay. We know we're going to have a liquid level in the boot. So there's the water level. Here's the oil level here. Just going to label that normal liquid level. Low liquid level. And my high liquid level. Like that. These are going to have similar indications on there. And we definitely are going to need to bring a feed in here, like that. So let's draw some nozzles. We're taking it's a three-phase separator, so we're taking vapor out as well. Let's draw some nozzles here. Let's put our outlet out here by the low liquid level, and this one there. I think this might not be a bad idea to have an internal nozzle. A little sketchy. Okay. That way, we know we actually have two-phase flow going into the vessel because we're dropping pressure. So we'll turn that, and it'll basically hit the edge of the vessel here, and vapor will go this way, and the liquid will kind of go that way. So you don't really need to draw those arrows, but I just kind of I'm trying to think about what's happening in the vessel with the fluids. Did you guys put a demister in it? Yeah? Okay, so let's draw a little demister here. Like that, probably a good idea. Okay, so that's the major nozzles. Then we're going to have to put some instrumentation on and stuff like that. So I want to leave myself lots of space around here to do the instrumentation. But let's go and think about this lock on me. No, I'm good. Okay, so the next piece of equipment is essentially a cross exchanger where we're cooling it off a little bit more, are we? 160, 103. No, we're heating it up. Sorry. Okay. Okay, what kind of heat exchanger did you guys use on the oil?
For the process cross one?
Yeah. Yeah. That's the three-phase separator preheater, I think it's called. Preheat?
Two-phase separator?
Two-phase, yeah.
I think we were just going with a double pipe for this one because it was such a small area.
Oh, was it?
Yeah.
Oh, okay. What's the duty on it? What did anybody else use for their heat exchanger there? It's 700,000 BTUs an hour, almost a million BTUs an hour. What did anybody else use for the heat exchanger? The oil comes off this and goes into the two-phase separator. What kind of heat exchangers did you guys use? A what? You guys used like a BEU or something like that? An AEU or something? Let's try it as an AEU maybe, just for fun. Okay, so the AEU has a flange on the end, like that. And we need a set of flanges on for the tube sheet. Like that. And it'd be great if I could get that level, eh? Let's try and get that a little more level. There, now I can see it. Parallels are being too tall, eh? Okay. Just gonna draw some tubes in here. So if you did it with a double pipe, then just draw it on your P&ID as a double pipe, that's fine. Okay, which side? Okay, we're gonna need some flanges here. I need to know what side to put the oil. That. That look pretty? Good enough? Okay, now we need to, what I'm thinking here is I've got to bring lines in to get to there, and lines are going to go out here. And come out here, and we're flashing, so we want to put the two-phase separator probably right here. Like that. Like that. Let's draw the liquid level in here. I'm going to bring my feed stream in above the high liquid level. That way we don't get any coffee pot problems. Gurgling the liquid right out through the top. Like that. We may have a demister in this one, so let's put that in there. I assume did you guys do demisters in this? Okay. It's good. And we have one more heat exchanger, right?
The trialene acid.
Okay, so we just need a little cooler there. Let's move that. We could go down here with it, or we could go up here with it. Seems like I have lots of space up here. So let's put it up there. This is kind of one of those cases where I almost would say let's just split the P&ID and put the cooler on another P&ID, but we'll do it anyway. What kind of heat exchanger? Is that a small one as well, or?
It was a little bigger. We're going with BEU, I think.
You went BEU? Okay. Excuse me. Okay. Okay. We're in good shape now. Okay, so we have the equipment laid on. Now we just got to put the process piping on. think about this. So let's talk about our feed stream. This feed stream is coming from where, you guys? It's coming from a cross exchanger right after the reactor. Okay. So, and there is a letdown valve on that somewhere in that system. So we either put the letdown valve on our P&ID or we stick it on the previous P&ID. It's going to be a little bit easier to put it on the other P&ID in terms of space. We actually have it shown on sheet 5 for this one. You got to make a decision whether we're going to put that control valve on this P&ID or not. I suspect because it's there's a lot of pressure drop, there's going to be a fair bit of flashing. We probably want to put that control valve as close to this vessel as we possibly can so that we don't have a lot of two-phase flow in the lines. So if that's the case, I'm going to do it right here. We might even put it right up against the vessel, actually. No, we need it. We're going to need to do maintenance on that valve. Okay, there's my control valve. So that's the. Remember, that valve is letting pressure down from about 3,000 psi to what are we? About 3 atmospheres in here, something like that. 4 atmospheres in here. So there's a lot of pressure drop across that. That means we're going to need to do some maintenance around it probably. So we're going to need reducers around the valve almost certainly. It's going to be at least a couple of line sizes smaller than the flow. We're going to need to do maintenance around it, so we better put some isolation valves around it. We might even need to have 2 valves. We're either going to have, in order to do maintenance, let's show it as a double control valve system. Just because I think it's going to be really prone to erosion. This a little bit. That. And moving that one too. Yeah, you could. You could put the block valve. You mean the block valves? You mean? Oh, put the reducers here.
Yeah.
Yeah, you could. You probably could. This is probably the more common arrangement, like this. But because we're trying to kill pressure, I could see us actually. I could see us also putting the block valves inside the reducers if we wanted to. But this is, I'd say this is the more common way of doing things. So that's all very good. We're going to need a controller here. Now that controller may not be on this P&ID. So we may want to show the controller on a different P&ID. There's a chance you can either select the valve with this control block, or you could probably do it right as part of the controller. If that's a LIC or an FIC or whatever it is, let's make the selector an HS. I think about how I want to do that. To select, what I'm trying to do is just trying to represent the fact that the operator can select which valve they want to control the system off. So we could have two controllers. Actually, that's maybe the better way to do it. We'll just do it as two controllers. And then it's easier to do probably a bumpless transfer. So this one is going to be off this one, like that. Like that. I didn't really want to get into the controls, but at this point in time, but there, I've got it. Yep. Why would you mechanic? Why wouldn't you? Yeah, well, the controllers don't cost very much. They're just software. The valves are costing a lot of money, though. So yeah, that's a debatable double control valve. Like that, you're only going to do that because you think you have so much wear and tear on those valves that, and you want to be able to operate the system constantly. If you might sit down with the instrumentation people and talk about, maybe using a very special hardened steel valve or something like that that can handle the erosion, and maybe you don't need that second valve. You just shut the process down, change the valve out. You could have a shop spare as well. You could just get rid of that. Get rid of that one control valve, and you would just shut the process down and have an arrangement where you could swap that valve out fairly quickly. If it's a small line, you might be able to swap it out fast enough that you were not going to have a big interruption in the process. I'm going to leave it for now, but I think it's definitely something that would require a little bit of discussion. Okay. The easy one is the water, because it just goes right off the P&ID, right? Yeah, it goes on to sheet 3 where there's some cross exchangers and stuff like that. So we don't have to worry about it on this P&ID, so we might as well just, we probably want to have a manual isolation valve on the piping. So not a control valve, just a valve to isolate it, and then because I'm not going anywhere with it.
Do things always have to leave the right-hand side of the page?
Yeah. Yeah. Okay.
They always have to leave the right-hand side?
Yeah, you want to come in from the left and leave on the right-hand side whenever you possibly can.
Like the furthest right?
As far as you can. A nicely laid out P&ID. You'll see things lined up on the P&IDs. Like somebody that's really artistic at doing P&IDs, you'll look at them and it's a little hard to tell, but they'll have balloons and line numbers and things like that lined up vertically on the P&ID. It just makes it look it makes it easier to read and more aesthetic. So I'm going to have trouble doing that unless I do. I might get away with that by doing this. I'll try and do it actually. Okay, so this is going to sheet 3, and this is recycle water. Another thing that people will sometimes do is they'll either letter code the balloons on the edge of the P&ID so that you can connect to the other P&IDs. Another thing people will do is they'll put the line numbers on here, and then you can follow the line number from one P&ID to the other P&ID. Okay, so that's the water. And now we are into, actually, might as well do the vapor phase, right? The vapor phase is just ripping right off the P&ID as well. Yeah, okay, that's easy. So we might as well go up and scoot across the top. I'm going to be crowded in here. I can see it already. So I could come across here and go out that way. I think out and top is the best way. I almost need to move this. I might want to move that down a little bit. Okay, let's put another valve in here. And I'm going to line that up. That. Vapor to, where's it go? Sheet 7. It's recycling back to the ponds, really, isn't it? Yeah, vapor to ponds. Not sure what the sheet number is, so I'll just leave it blank for now. Okay, now, one thing I can see right away is I'm putting enough block valves on this vessel that it's going to be isolatable. It's going to be isolated at some point in time, which means, and it's a fair sized vessel, which means I'm going to need a relief valve. So I'm going to put it on right now. So I'm going to put a nozzle on. And the relief valve like this. I'm just going to vent it to atmosphere. It's mostly water. If it were to blow, actually, if it were to blow, there's a couple of different reasons why that thing could blow. It could actually be a two-phase flow. That's going to get messy for the calculations. Luckily, we're not doing it. There is going to be some hydrocarbon, but a lot of water around. So I'm not sure how flammable that is. What you might end up doing is having a diked area and then just dropping the relief valve down into the diked area. That might be something we need to do. So we're going to, maybe what we'll do is we'll say two diked area. That's a little hard to read, I'm sorry, but okay, well, we can fix that. We'll just make it. That's why we're using a whiteboard, Dave. Okay, and I'm not going to put an isolation valve on that relief valve. We need to do maintenance on the relief valve like once a year, so I'll just shut the process down. We're going to shut the process down in the wintertime anyway, so I don't need an isolation valve there. We'll just do the maintenance then. That makes it a little bit safer. And we're getting in pretty good shape here, actually. Okay, so now we got the oil. And we know we're going to be flashing through here. So that means what I really want to do is I want to come up from the bottom of this heat exchanger on the shell side, because I can flash in the shell side, I think, better. What side did you guys put the oil side on your heat exchanger? You probably didn't really do it. Or did you? Oh, you're double pipe, right? Yeah. What did you guys do? Anybody?
Would you want to show where the stuff going to the reef, like in the event that the valve kind of opens?
Yeah.
Do you want to show where that stream's going to go?
I just wrote it. I said to the diked area.
Okay. So
Yeah. I could draw a dike on here. Sometimes we'll do that. So if I was going to do that, I would draw a little dike like this, like that. And I would just draw this down and come down in here to diked area. I'd draw it. If you want to make it pretty, you kind of draw it like concrete. So that would be another way to do that.
Would that be typical or not?
Yeah, it's pretty common to do that. It's a mixed bag of like if you look at the Verison P&IDs, I think they probably have lots of diked areas, but I don't think they show any of their diked areas in their P&IDs. So it could go either way. Yeah. Okay. I know I'm going to be crowded, so I'm just erasing that out of there for now. Okay, so do I want to put isolation on there? Yeah, let's do isolation. Okay. Gonna come down. You notice how I'm giving myself lots of space around this equipment here? What I'm asking myself right now in my head is, do I want to put an isolation valve on this heat exchanger or not? And I am inclined not to right now, because I'm isolated here. They're pretty close to each other. I'm not really that worried about it.
Do you have any particular guidelines for when you would not want to?
I'd say the general rule is to put isolation on stuff. If you really want to avoid putting a relief valve in, then you need to get rid of the isolation valve. Let me draw this up here. I might rethink it. As I'm doing stuff, I sometimes rethink and I go back and I put isolation valves in. So this has got to come out of this heat exchanger, and we are actually vaporizing it through that heat exchanger, right? It's not, we're actually putting, oh, wrong one here. We're putting a fair, not too much heat, but a little bit of heat in there. So I might actually want to indicate the fact that the line needs to slope up to the two-phase separator. If that's the case, then I draw a little triangle. That just makes sure that as it's vaporizing through the heat exchanger, coming up through the piping, it'll slope up to there, which is probably going to put this heat exchanger at a low point. So in order to drain this system, we may need to add some drains at some point in time. I could show that now. Just put a small valve in here. There's my drain. And the other stream on that heat exchanger is essentially coming off the bottom of the distillation tower. So it's coming off one of the P&IDs you guys are going to do, and then it's going up to that heat exchanger there. And that's essentially cooling it. So do I want to come in this way and go up to that? I think I can do that. Okay, so I forgot to put that heat exchanger in there. My bad. The preheat algae slurry 2. Ooh. Slurry 2. Sheet 3, I think it was? No, sheet 2. Sheet 2. Sheet 3. Sheet 3. Okay. And this is coming from okay, so I'm just about to cross a vertical line here, and horizontal lines break vertical lines. Bam, bam.
Why is it sloping? Because it's two-phase flow?
Yeah, it's sloping because it's two-phase flow, and I want to make it bent. Yeah. Yeah. Okay, so this is coming from the column. from column bottoms. Sheet, I think it's sheet 6, right? Yes, sheet 6. And then we've got cooling water on this piece of equipment here. Presumably the cooling water is going to be dirtier, so we're going to put the cooling water on the tube side. This is going to come up here into there. And this is off to, there's a whole control system on the back end of that actually. So not so easily. I think we're recycling it into the pond partly. Is that right? Oh, we're back in.
Is there a rule to where you put arrows?
No, actually is there a rule?
To arrows, like if you're putting an arrow
Yeah.
into that.
Yeah, normally you probably don't put arrows there. Sometimes people put arrows here just to kind of get a little bit of direction of flow. I'll probably erase that if I'm going to put
So would you usually not
a valve in
put
there.
arrows at all? Is that okay, or should you?
It's okay not to put arrows in. It does make things a little bit simpler for people to read. So sometimes people kind of put arrows like that just to make it a little easier to read. Okay, this is going back to the main high pressure pump, which is called the HTL feed pumps. Okay. Just like that. Sheet. What is that? Sheet 2. It's right there. So that line there is coming on. Oh no, we actually came back into the tank, didn't we? And then we changed it on the process hazards analysis, I think. Yeah, I think we might have come back on here. So we actually have to mark this P&ID up to make that change. So it's got to come in from basically here. I'm not going to do it right now, but you want to kind of note that. So we fix that P&ID. And then we also have, I think we have a, we have one of our purges in the process on this P&ID. So that's fairly important to get on there. So I'll just draw it this way, but I know I have to put some controls in there for sure. Okay, and so this is, that's going to go to waste treatment. Okay. A few other things that we're missing here are this. Line that up like that. And this. Line that up like that. And the vapor is heading off to the ponds like that. And this liquid is going off to the heat exchanger called the column preheater. Sheet 6, right? Yep. And then we're just missing some cooling water. Cooling water should be coming in here. Of course, I crowded myself out with my controls. That was clever, wasn't it? They're gone. Cooling water supply. there's a couple different styles of P&IDs. Sometimes people will show utility headers that just rip right across the P&IDs. So they'll have a cooling water supply header that goes across there. And then if they've got a lot of heat exchangers, they'll just drop off the cooling water supply header to the various pieces of equipment. And they'll probably have the cooling water return header along the top as well. It's not really a good idea to do that because what happens is the order of the branches is relevant on a P&ID. And so if I showed the cooling water header going along here and I dropped off to say a heat exchanger here and another heat exchanger here, then it implies that it's got to be piped that way, that this heat exchanger's got to come off the cooling water header first and then that one come off second and that one come off third. And that may not be the most economical way to actually lay the piping out. So it's better to actually have another P&ID that would show the cooling water header systems, and that utility P&ID would then show the branches after somebody's done a little bit of design around the most economical way to route the piping. Okay, so now this is a utility line, and this is a main process line. So some people would actually break the utility line around the process line, but it's a major line, so I'm going to follow the horizontal versus, whoops, hang on.
Would figuring out the economical layout of the piping be the role of a process
No,
engineer?
no,
Who
that's
would be responsible for that?
That's going to be the piping designers that are going to do that. Yeah. And I don't like that line. I want to fix that. I want to make that more horizontal. There. Okay, so that's my cooling water supply, my cooling water return. Man, I really cramped myself in there. Well done. This is why you need to do this as a rough sketch first.
Isn't it counter current flow? So shouldn't the cooling water go to the top?
It's a YouTube, so it won't make any difference. So, like the cooling waters, if it comes in here, comes out here, and goes out there, this is going to be crossing that way, so it won't make any difference. What sometimes people will do, though, is they'll feed the heat exchanger in from the bottom so that when you're flooding the heat exchanger with cooling water, it actually is self-venting that way. If there's any air bubbles that come in through here, they'll basically work their way out through the heat exchanger like that. Okay, I know I need a control valve on there. I can put the control valve on the inlet, and I can put it on the outlet. I was planning on putting it on the outlet, but I've really cramped myself in here. So now I'm trying to figure out what the heck I'm going to do, other than actually move the whole thing down, which I don't really want to do at this point in time. But what I can do is I can come down here and put the control valve kind of in here. So I'll get away with that, but it's not maybe the best. It's not the best way to do it. Actually, it's going to look really good for the controls. And here's my cooling water return. Okay, that's the major piping. How are we doing for time? It could be a little better laid out. Let's get some controls on here. Let's start from the left and work from the right. So we know we had those controls on there. I can redraw those now. Like that. Probably the best thing to do would be to make these valves fail closed, I think. If we have a problem, The last thing we want to do is start dumping 3,000 psi high temperature, almost just subcritical water into that vessel. So I want to bottle the problems up back here. All through here. Okay. Let's see. This has got a pressure control system on it. We know this has a pressure node on it because we determined what the pressure was in the simulation. So in order to do that, we're going to need a pressure transmitter. And I want to be able to maintain the pressure transmitter, so I'm putting a valve in, putting it as an indicating transmitter in like that. And I'm probably also wanting a local pressure gauge. So I'm going to put a PI in. I'm going to need a control valve in here. I've got lots of space right now. Let's put it in here. And do I want to fail that open or do I want to fail it closed? That is a good question. When there's a problem, do I want to just automatically depressurize that, or do I want to bottle the problem up in the, that's where you need to sit down and do a little bit more analysis of the safety systems. You kind of need to understand what's going off, where that stuff is going to. I think I'm going to make it a fail closed. But one thing I could do is put this on hold for further discussion. Hold valve failure. For PHA analysis. Just do that. It's a little bit of a cheat. Okay, we need a pressure controller. That's easy. It's going to be in the DCS. That's a lousy DCS symbol. Let's get that. Let's show that better. Okay, like that. We want to have a pressure alarm high and probably a low. Like that. Do we need any interlocks on the pressure? What would we do? If we found the pressure started to get high on us, it might be because this valve is sticking. There's not much we could really do about it. We could shut the pumps down that are way upstream.
Is there no symbol for a pressure alarm or any sort of alarm? You just put it kind of off the corner of the box?
Yeah, you can. There is actually an alarm symbol if you want to. You can do. You can do this. So if you're gonna drive a function off that alarm, then I would show that. So let's say we want that. Say we have a high alarm and we have a high high, and when it hits the high high, we want to have some sort of trigger in the control system. Maybe we want to shut down the feed pumps. Maybe we want to shut the heat off somewhere. If that's the case, then essentially we're really building an interlock system at that point in time, but we're doing it with a basic process control system. But if we do want to have something driven off there, that's when I start to show the alarms. If it's just a simple, like a bell ringing on the operator console, then we generally just show it like that. So it's two ways to show it.
If you were to send a signal off, say, to the feed pump, which is on a different sheet,
Yep.
Do you bubble that? Like, is it the
Yeah.
same bubble like
Yeah.
these, or how do you indicate it goes
Yeah.
to a different sheet?
You'd have to show it up, and you'd probably want to rip it right across the P&ID. Sometimes you'll cheat and just show it right here, but it's not good practice. It's better to pull it right across the sheet. I'm obviously never going to fit that in there, so we would say 2 feed pump interlock, 2 feed pumps. Actually, the other way to do it would be to just show it right as an interlock symbol. That might not be a bad way to do it. So, and that actually is fairly, so show it as an interlock like that and call it the feed pump shutdown. Feed shutdown. I think we even have an interlock like that, don't we? I thought we did. No, I guess not. We have a tank overflow. So, and then what you have is you have a set of notes somewhere on the right-hand side of the P&ID. So you do this. Feed shutdown. Interlock. Like that. So that's not a bad idea. Let's put it on there now, and we can always take it off later and argue over the best way to do that, the best way to protect this vessel from, say, a failure in one of these valves. Actually, if we're really worried about it, well, we maybe put another valve right there that we can just slam shut. Okay, so we had a pressure node. We've dealt with that. We've got pressure control there now. Is there anything else we need for the vapor system itself? We might be interested in what the temperature is on the vapor side. So we might want to just put a thermal well in and put a TI in there. You never have too many TIs. That's stuff usually I come back and do later on, but okay, I think we're pretty good there. Let's do the liquid system. Again, let's start with the water because that's easy. Now, we've got an oil-water system here. It's a real dog's breakfast of stuff. There's even probably some solids in here. So those solids and high molecular weight hydrocarbons and guck is going to screw up a normal level transmitter. So we're going to have to put a level transmitter in with seals on it. So we show a seal. I'll just draw it here. This is big. Just like just to kind of show like a diaphragm. Like that. Kind of looks like a flange, but it has that little squiggly line in it. There's the seal. Then we're into the level indicating transmitter. So on the transmitter side of the seal, it's oil filled. On the process side, it's got the water in contact with the seal. So that'll hopefully make the level transmitter more reliable. The other thing that we might be interested in is just what is this? We might want to walk out there and actually see what this fluid looks like. It's not super high pressure, so we might want to put an actual sight glass in there. So that's essentially a glass tube. Let's put some valves on there. Like that. And put a sight glass in. Like that. That'll allow us to actually look at the fluid, kind of like, you know, on one of those big coffee urns. You've got a glass tube. You can see where the liquid level is. So we'll be able to see the liquid level there. I might have forgot something here. I have to check with my instrumentation friends, but I think we need a valve on the inlet of the diaphragm seals. There. I'm not positive about that. I need to talk to somebody from instrumentation and just confirm that they would want to put a valve on there. So it's not really a big deal from the process point of view. It's really just making it maintainable. And okay. Not very pretty valves, are they? Okay. There. Okay, so the level transmitter implies we've got some sort of a control, so we need to put a control valve in. Let's drop the control valve in right here because there's lots of space there. And here we go. I've got a valve right there, so I'm not going to bother putting another valve. I'm just going to go down to the control valve here, down to pipe size. Put that in, go back up, pipe size, and put an isolation valve in here. That way I can pull that out. I need a level indicating controller. If I move this line over a little bit, that'll just give me just what I need for space. Perfect. LIC, like that. That. And this needs to come out here, come down through here, like that. And we probably want to have a level alarm, high, low, on that as well. So we pretty much want to duplicate the same thing for the oil, I would say. Now one thing is, I want to know that the level is getting close to that nozzle. And if I put the bottom level transmitter above it, then I'll never actually know. So I need to put the bottom level transmitter down here, down below the outlet of the oil. So I'm going to put a nozzle on here. I'm going to put my valve in and my diaphragm seal. I'm going to put another one in here. If you want to make these P&IDs really artistic, there's an old process engineer friend of mine who just finishes the nozzles off like this. Just puts like a little half oval. Well, you can see that, but it does actually look really nice. That's just artistry. Okay. We're going to need our diaphragm here. And our level transmitter is going to go right in here probably. Like that. We need our level controller. That. And we need a control valve on here. We can probably fit it in here. Actually, if we line that up, that would actually be really nice looking. Let's try and do that. That'll actually look really good. Like that. Oh, I need a valve. Like that. That's possible. I don't need two valves here. Yep. Ah. You see how it gets pretty cramped pretty fast, eh? This one and this one, you mean?
Yeah.
Yeah, probably don't need both. Depends on where the valve is kind of located relative to the system. You might get away with not having that.
To trans,
Jay?
Why is the level transmitter taking information like above the high liquid level? When do you want it like?
Oh, so the level transmitter is a differential device. Okay, it needs to measure the pressure above the liquid level, and then the bottom leg of the level transmitter is measuring the pressure down there, which is telling you.
So it should just always be above where the liquid is.
Yeah, it should always be above where the maximum liquid level is. Yeah, you want to get it way out of the liquid level. Yeah. Yeah. And because we're thinking it's going to be a dirty, we're going to put seals on as well. So.
Could the level, I like C for the bottom of the water is
Yep.
down below. Could that be used like by differential pressure?
Yeah, this is still differential pressure as well.
Okay.
That's right. So you're measuring here. You want to measure basically the pressure of the oil.
Yeah.
Okay. And actually, what's probably going to happen? No, that's all right. So as this level goes up and down, this pressure goes up and down with it. So that basically negates. So when you're trying to measure the liquid level down here, if the pressure up here is moving around, it gets compensated for by measuring that pressure. Yeah, so you're getting a fairly true measurement of where the level is down here in the boot.
So level controllers are always done by like differential pressure of the isolation.
Not always. No, there's lots of different level transmitters. There's radar. There's even there's capacitance measurements. There's lots of ways to do level. So this is the most common way to do level, which is differential pressure.
So we should just assume to always use that.
You can probably assume that you're going to use differential pressure. Yeah, yeah. Now and then what happens? You know the process engineer is going to fill in like a spec sheet with the information about those instruments, and then the instrumentation people are going to look at those spec sheets. They're going to go out and talk to the vendors, and maybe make some recommendations. They might come back to you and say, we don't want to use differential pressure. We want to use some other technology. So you have that conversation, but. At least people know you need that level. You need some sort of a level transmitter, and you've got the loop, the control loop defined. So every time we put a control loop in like this is like $10,000. $10,000. Okay, am I done that vessel? Oh, you know what? We don't have a sight glass on the vessel itself. So we can either show a sight glass out here. Sometimes you can kind of cheat and show the sight glass right on. I'm gonna show it that way. Like that. So that's just another way to show a sight glass when you start to get your vessel really crowded. Sometimes people will show the instrument kind of inside the vessel. It's not inside the vessel, it's outside the vessel. It's just that if you look at the end of the vessel, if you look end on, these transmitters might be like this. And you can layer them along the length of the vessel, like that. So the details of all that stuff is all shown on the vessel drawings. Okay, are we missing anything, you guys? Help me out here.
You need a manhole?
Do I need a manhole? Yeah, but you don't have to show the manholes on the P&IDs. Yeah, there definitely would be a manhole in there. Drains and stuff like that. We probably want some drains. We got to get stuff out of there somehow. I don't know where we're going to drain it to. You're not going to drain it to a bucket, that's for sure. Well, we can drain most of it out through here, so if there is any left, then yeah, we might just do it with we might want to just put a valve in and they can decide what they want to do later. So I'm going to put a valve, and then I'm going to put So that valve doesn't if that valve accidentally got opened, we don't want any spills or anything like that. So I'm going to put a what's known as a blind flange on the bottom of that valve, which is just a solid steel plate. It's just bolted onto the bottom of the valve. Anything else we might want to put on there? Well, if we do, we can come back and do it. Okay, so that's the water, that's the oil going out. So that's giving us level control in the vessel. Basically, it's going to go through the heat exchanger, come out here. We might be interested in what the temperature is on this. So we might show that. We're not necessarily going to control it. We just want to know what it is. So I'm just going to put a TI in there. We might actually be interested in what the fluid temperature is in the tank or the fluid temperature that's going into the heat exchanger. If that's the case, let's put a TI in this. And we're going to pull it into the DCS. There we go. Now we can monitor the temperature. So presumably that temperature is pretty much the same temperature going into the heat exchanger. Oh, okay, one thing. When you're doing temperature, in order to make the response of the temperature fast, they'll essentially always put, you've got I didn't bring it with me. Okay, you've got a probe that's actually the sensing device, okay, like the RTD or the thermocouple or something like that. And it's embedded in the pipe. Whoops. So there's the pipe like that. And what they do is it'll be mounted in a thermocouple like this. Sorry, a thermal well. Thermal well. So this is just, they drill a hole in the piece of steel and then they put a pressure containing device, and then the TE, which is the RTD, can just pop in and out of the thermal well. And what they'll do is they'll always, whenever possible, they won't put it in a straight section of the pipe. They'll put it right in an elbow where there's lots of velocity and lots of turbulence. So that just improves the heat transfer around the thermal well and gives you faster response. So that's why I showed the TE in an elbow, like that. Yep. Would you ever have a TE without a TI? Like that? It's possible, but it'd be pretty unlikely. So you might put the TE in and just leave it like bare wire, and then somebody would have to walk around with a handheld device, plug it into the handheld device, and then they can measure the temperature. So if you're trying to save yourself money, because that wire, to go to that TE back into the DCS, you're going to have to pay for the wiring and the conduit and the software configuration. So you might save yourself, I don't know, a couple $1,000, not that much. So
not every 2
So I would say for you guys, every TE would come with a TI. So I've very rarely seen us put a TE in and not wire it back into a DCS.
Yeah, I was just gonna, I guess the question goes back to why not just have one symbol for the two, basically.
Oh, okay. So what you have to understand is the way design is done. Every one of these instruments is going to be given a number. So like this is going to be, I don't know, this is a flow valve or something. This is flow valve 100, and this is FV 101, something like that. And the level transmitters are going to be given numbers. The TEs are going to be numbers. And then they create a big, huge spreadsheet with all the instrument tags on there. And so all this field stuff has to get purchased. And so they need to know to purchase the TE. And essentially, they're giving it a number so they can track it, so they can actually purchase it. This one, let's call this 150, you know, TE 150. This is TI 150. It's just a way to track all the tags, all the instruments, and for people to understand how much work is required to do the construction, do the design and the construction. So they're going to split this stuff up so that people know that they've got to buy a TE and what the TE is, and then the software configuration has got to be done. So they're going to break it up just for the design and construction.
Is that TI on the top of the three-phase separator? Is that also supposed to be a TE and TI?
No, that's just a temperature gauge. So you can have a TI without a TE. Okay, so a temperature gauge is literally like a thermometer. The same way a PI is a pressure gauge, it just reads locally. Okay, it literally is like, it's a dial with, like, that's a thermometer, right? And so that is that. Where a TE doesn't have any indication, it's just a blind thermocouple RTD, and it's got to be wired back to the DCS before you can actually see it. So this you can actually read when you're standing out by the tank. That you cannot. A TI can generally not. You can turn, what you can do is you can provide a temperature indicating transmitter. So most of the TEs are just wired straight back to the DCS, and you don't need a transmitter, unlike level and pressure. If you really want to be able to read the temperature out in the field, then you put a TIT in. So if you wanted to do that, let's say we did, just for arguments. So it'd be simple, you just do a TIT like that. Yeah, not very politically correct, sorry guys. But that's how you do it. So that would give you a field indication of temperature, and it'll also pull it back into the DCS. So if you look on the Verison P&IDs, you'll see that. Okay, so we're getting there. That's the oil down in. We don't care about the temperature. What we might be interested in actually are some pressures. So you know the heat exchanger, if it's fouling, the pressure indication, the pressures are going to change. So I'm putting some pressure gauges in like that. I'm probably going to do the same thing on this one. Like that. This is going off into okay, now if we actually want to control the temperatures here, we've got a bit of a problem, don't we? Because we have stuff flowing through this heat exchanger. We have no way to control the temperatures. So you got to ask yourself the question, do we care about the temperature here or not? Do we want to be able to, if it gets a little higher than we think, is that a problem? Is it not a problem? If we're really worried about that temperature, then we somehow need to change the duty of this heat exchanger without actually manipulating the flow rates through the system. How do we do that? Generally, with a heat exchanger, right, you modulate the flow rate of cooling water through it, and that adjusts the temperature on the other side. How do we do it with a heat exchanger that has two process streams? Any thoughts? You want to know the answer? Or should we let you guys puzzle over it for a day? Put a what, sorry? You could put another heat exchanger in, yeah.
Is it because one of those streams is more important than the other stream, so you can control the one that's less important? Because the one downstream going to
Could be. Could be. Problem is, like, this is coming from the column bottoms, right? So if we put a control valve on that column, on this line here, we're going to get ourselves into trouble because the column bottoms is going to have level control on it. So if we put a valve here, there's going to be another valve on the column bottoms level, and we're going to have dueling control. If we put a control valve on here, then we're going to be basically fighting that level control. So somehow we need to manipulate the flows through the heat exchangers, through that heat exchanger, without manipulating the total flow. Say again?
Could you add a hold-up tank somewhere?
Maybe. Hold up tank. Got any other clever ideas? Bam. Put a bypass in. Put a bypass in, then we haven't manipulated where we can put a control valve on here, like that. Obviously, I'm a little bit boxed in here a bit. We can put a valve in here, which can allow liquid to bypass around that, and so you don't get as much fluid going through here. Clever, eh? Well done, Chris. So now what we can do is, depending on which one we think is more important, maybe this one. Make that a fail-closed valve. I forgot my failure positions on these valves too. Okay. So yeah, a bypass. That one is a little bit of lateral thinking. The problem with that is if you have a really low pressure drop through this heat exchanger, then it's quite hard to actually get the fluid to bypass the heat exchanger. This heat exchanger has to have a fair bit of pressure drop for that game to work.
Do you always bypass the tubes?
Now you can bypass either side, wouldn't matter.
It doesn't matter.
Doesn't matter.
Is there one where you usually choose a bypass for, like the more important stream or something like that?
It's a good question, Jay. I don't. What's that?
The next heat exchanger, you can control that with as much as you want to, you can just use cooling water.
Yeah.
So you might as well bypass it on that stream if you don't really care about
Yeah.
this temperature.
Yeah, that's why I'm putting the controller on this stream here for sure, because that one I can control with that heat exchanger. Yeah, the bypass, you're gonna end up changing these two temperatures together when you open and close that bypass. So whether I put that valve, whether I put the bypass on this stream or put the bypass on that stream, I don't think it really matters. Can we think about that for a bit? We can talk about it later. How's that sound? If I make any mistakes and I go back, then what I'll do is I'll mark them up with a red marker over the week, because for sure going to miss stuff on this in this game. There's no way I can go through a P&ID like this and not make a mistake. Okay, so we got this going in here. We're into here. This is a no-brainer. This is still going to have some solids and some guck in it, so we better give ourselves some seals on this one as well. Any other good questions? You guys are asking good questions, by the way. And I know I'm going to put the valve in here. I'm going to make it fail closed. Like that. Level alarm high low. Okay, that's good. This has got pressure control as well, so I need a pressure transmitter. So once you've done this a couple of times, you kind of look at these things and you go, yeah, I know I need that. Like that. I need a valve in here. I'm a little cramped. Yeah, let's do this. I'm going to fail it closed. Like that. Put my PIC in here. Pressure alarm high low. Like that. Like that. So, and then if I was going to redraw this on a nice big sheet of paper, I'd obviously just space stuff out once I know what the instrumentation looks like. Okay, so I've got my level control here. I've got a pressure transmitter here. If you're worried about this being a really dirty stream, and you're really worried about, say, the mist eliminator plugging on you, then what you can do is you can put a differential pressure measurement across those two. So pressure differential indicator. I don't think we really need to worry about it in the DCS because I don't think it's going to plug very often. So we'll just make it a local indication. Operators can walk out there and check it once a shift or once a day. That might be handy to know. If you know it's clean service, you wouldn't bother with it probably. Be worth having. Have we got isolation on this? Yeah, probably. So let's put a relief valve on here as well. You're probably legally going to need a relief valve on the heat exchanger. That's going to get complicated. Okay. And this is all vapor, so we're just going to vent that to atmosphere. It's mostly just water anyway. So I don't think we need to flare it. If we did need to flare it, if we're worried about what's in here, actually, well, it is oil, actually. Okay, so what we're going to do is we're going to vent this to a safe location. So if it was natural gas or something like that, then you definitely need to vent it to a safe location. That. Are we worried about the temperature? No, we got the temperature there. Are we worried about the temperature coming out of here? Probably not too much. We don't have any other worries, so we're almost done actually. Did I miss anything? We need cooling water control on this heat exchanger. We haven't got there yet. Yeah, we're not doing too badly. Okay, so this one is up through here, out through here. Okay, we're gonna need some controls there. So we just basically need to measure the temperature and get that into a controller there. Likely I'd put it right here. So I'll show it as a TE like that. Pretty crappy, eh? Get my T, this is a TV. This is a TIC. That into the control valve. It's cooling water. I'm going to fill it open. That way, if it is hot and we have a failure, we're dumping cooler water to the waste treatment plant. We're not going to kill any bugs or anything like that. And it would be smart to have some PIs on this, like that, another PI on here. Like that. Okay, now one thing, we have our purge, and so that's going to need some control on it, and we got to decide what we're going to tie that controller to. I'd say we're going to fail that closed. I think because it is just a purge, we can just set what the mass flow rate is, and we're not too worried about what the actual flow rate is. So we're just going to use a low-cost flow meter. We're not going to use a mass flow meter. We're just going to use orifice plates. So I'm using an FE and an FIT combination into my FI flow indicating controller, like that. Like that. I don't even really think I need an alarm on that. I don't really care what the flow rate is. Maybe if it got low, I'd maybe want an alarm on it, but that's pretty good there. We probably want an alarm on our temperature, so let's put a high and a low alarm on there. That's probably handy. There you go. Alarm high there. And okay, so we've got our cooling water. We probably want to put some just manual isolation valves on the cooling water, just to be able to isolate the heat exchanger like that. And we might even want to do that on this heat exchanger as well. So man, I really boxed myself in here. Knew I shouldn't have drawn it so close to the edge of the heat. There. Dodgy, eh? Okay, let's just move it down the pipe a little bit there, and we can put a PI in there as well. So if you put the PI on the downstream side of the block valves, then you're measuring. In a sense, you're not really getting a true measurement of DP across the heat exchanger. You could actually put the PI on the heat exchanger itself. So that might not be a bad idea. Actually, I like that idea better. So that allows me to put the block valve right on the flange of the heat exchanger. And then we'll just put a PI right on the heat exchanger. No, I don't like that either. That's going to cost money. An extra nozzle on a heat exchanger is just costing money, where we can stick it on the piping for a lot less money.
Do you need that extra isolation valve on the PI, or do you already have the isolation valve coming out of the machine?
Here?
Yeah, like do you need both of those?
Yeah, this is like a 3/4 inch, and this is full line size. So this could be, I don't know what our flow rates are, but this is off the column bottom sheet. We're like 6,000 kgs an hour or something like that. So this is probably, I don't know, 2 inch or 3 inch or something like that. Where that's just a little valve. You can look around this room actually, and you can see some PIs in the chilled water system. I think I'm actually done except for interlocks, you guys. So we did put one interlock on here. If we're really worried about this level transmitter maybe not working, then we might want to put a level switch low on this. If we did, then we tie it into a level alarm low, like that. And then heaven knows what we would actually shut. We could shut, since that's coming from here, it's possible that it's getting low because that is closed. So we don't want to close that, that's for sure. It's possible that it's a problem because of that. Is open. If that valve is failed open, then there's something else we'd have to do. We'd have to put another valve in. I don't really see it being a major problem. We would just end up basically blowing vapor into the column. And I don't see that as being a huge deal. So I'm just going to make it an alarm. And since I've actually got an alarm there, this will have to be a low-low. So I've got a low on the transmitter and a low-low on the level switch. Can I see any other real issues around interlocks? I think the biggest problem I would see here is a problem with those valves failing or sticking open and us overpressuring this vessel. We've got the relief valve ultimately to protect us. So if I'm really worried about that, then about all I can really do is put another block valve in here. So this would be basically an emergency valve, and we're going to tie it in maybe to that interlock. So what I'm going to do is show that interlock FSD sending a signal into this valve. So that would, if we do get high pressure, then as long as it's not a fire under the unit, then that pressure almost certainly must be coming from the upstream side. We're going to shut this feed pumps off, and we're going to isolate it with this valve that's normally stays open all the time, and it just is a gate valve that would close. And we haven't shown any cascade loops. Actually, that's bad. We should at least put a cascade loop on so you guys know what a cascade loop would look like. I can't even think of where a good application of a cascade loop would be here. We can put one on just for argument's sake, but I don't think it's really all that useful. So if you did have to put one in here, let's say you wanted that level to go up and down. Actually, this is a good application for a cascade loop, because we'd actually like to have a nice constant flow into the column preheater, into the column system. And this is essentially dictating that. There's some hold-up time here. So the way to steady that flow rate out would be to put a cascade flow loop in. So that's easy. Put an FE in and an FIT. And then we'll put an FIC in, like that. Yeah, this is actually not a bad idea. And the level controller now has to send a signal into the flow controller, so that's going to be done, because it's all internal to the DCS, it's going to be done with software. So I get rid of the dash line, and I use dash dot. Dash circle, actually. And then the flow controller becomes the interior. Oh, and by the way, you guys are asking, Shing, you were asking the question about the cascade control. I got an answer back from a friend of mine who does a lot of DCS stuff, so I'll show you that afterwards. I'm a little late, but I think I'm done. If I missed anything, you'll see, we'll mark it up. We'll tell people to please leave on. Whoops. On. There we go. Anybody see anything I missed? James, did I miss anything? Do I want a relief valve in the heat exchanger? Yeah. You know what? I don't actually think I need one on the shell side, because I'm relieved through here. I can relieve through there. On the water cooler, oh, I should put some names on this. Yikes. This needs some names. What's this heat exchanger called, you guys? It's the, you guys?
Cryolene oleic acid cooler.
Oleic acid cooler? Okay, this is called the two-phase separator? Or is it got
Column feed two-phase separator.
column feed? Shorter names would be better. Separator. Might want to put the equipment number if we had equipment numbers on here. Okay, you kind of get the idea. We should do the same for all the pieces of equipment. And then relief valves on the rest of the heat exchange. So I'll have to think about that one. So there is a legal requirement to put relief valves on vessels that can be isolated, and heat exchangers are considered vessels. There are some companies that just decide not to do it. So, yep.
Is the interlock essentially just like a overriding like safety thing?
Yeah.
Like what it is?
Yeah, it's essentially, yeah, bad examples maybe, but essentially, yeah, it's measuring something and it's activating a control system to isolate the source of the problem. If we're really worried about this as an interlock system, like in terms of overpressuring, it might be because this pressure transmitter has got a problem. So a better way probably to do this, or a more safe way to do this, would be to actually put a pressure switch high in and tie that into the interlock system as well. So now that we have no indication that the pressure switch high is actually activated, so we might actually want to send a signal into the DCS as well. This can be pressure alarm high, like that. And so now we've got the transmitter that's sending a signal to the controller, and the controller can activate the interlock system. We also have an independent pressure switch high. And you notice I didn't put an isolation valve on that pressure switch high. So there's no way for an operator or anybody else to bypass that pressure switch high. Any other good questions, comments? James, anything else I missed, do you think? The what, sorry? A what level? Oh, a drain valve. Yeah, sure. Yeah. Yeah, it's good to have some drains and things like that on these things. So spare nozzles are never a bad thing on vessels. You never know what. Sure. There we go. A little drain. Just make it a 1-inch valve, something like that, or a 2-inch. Actually, if it's on a vessel, you make it minimum nozzle size on a vessel really should be like 2 inches. So otherwise they get bent when they're being transported around. A 2-inch nozzle is really sturdy. All the level transmitters are all 3-inch nozzles. All the PIs are generally 2-inch. Or sorry, the PIs are generally 3/4 inch when they're on a piece of pipe. So I can show you how to size the lines later when we get to the pump sizing and stuff like that. You guys don't really need to worry about line sizing at this point in time. Anything else I missed? Any other questions? So it looks pretty like if you just had walked in the room, it would have been really, you'd be scared, right? But when you start to just work it up from the basics, it's not that intimidating. You kind of understand what's going on. No, that's